Welcome. Welcome to the lubrication reliability in the time of COVID-19. Today's discussion will be focused around oil condition monitoring by Matt Spurlock of Delta P Reliability Services. This webinar will last approximately 59 minutes. There will be a quick, short questionnaire at the very end, so please stick around. Hopefully, we'll be able to answer some questions in the chat line. Matt will be focused on providing his presentation, but there may be an opportunity to speak at the very end. We'll definitely cover a lot of these questions and ideas and comments on the roundtable on Friday. Now, please join Matt in his discussion on oil condition monitoring. Morning, Matt.
Thanks, Michael. First off, I want to welcome everyone here and thank you for taking an hour out of your day to listen to me present this material on these inline sensor technologies and how they might be utilized in this time of COVID-19. I'd like to introduce a little bit about me. I've got about 28 years involvement in oil analysis and industrial lubrication, 8-year Marine Corps veteran. I was a mechanic on amphibious assault vehicles. So I've turned wrenches on diesel engines, transmissions, hydraulic systems, propulsion systems, track systems. I've gotten my fingernails dirty. So I'm not just somebody that read a bunch of books and said, oh, this might work. I've actually been there, done that on a lot of similar type of equipment that our customer base and our attendees are dealing with today. At one point, I had just about every reliability certification out there. However, I've maintained my machinery lubrication engineer, excuse me, and my analysis and technician certifications. I'm a trainer, author, presenter. I've had the opportunity and the privilege to be a keynote speaker at a distributor conference a few years ago. I'm currently the founder and president of Delta P Reliability Services. And what Delta P does, what I focus my efforts on is really staying involved, very deep involvement in the R&D of continuous oil monitoring sensors and trying to work on how we take that data and integrate that data with what we might see from a commercial laboratory. So I've got a in-house testing equipment. It's really a nice setup, and I actually get to have fun every day. And I think my biggest success right now, the thing that I'm the most proud of, and I wish I could have stuck around to see this development through, is I was actually able to contribute to the development of algorithms that help to answer the proverbial question, how much time do I have, or what's the next sample going to look like? Well, I was able to help develop an algorithm. And at the time of that I changed my focus away from that particular project, we were able to answer what the next oil sample is going to look like with about an 87% accuracy level. So that was kind of cool, and it's kind of a neat feather to have in my hat. So we'll go ahead and get. So hopefully everyone's staying safe. Staying healthy. Hopefully your families are healthy and things like that. So the things that we're going to talk about today include current challenges in today's COVID-19 environment. These we had challenges before COVID-19 that we'll discuss, and because of COVID-19, some of these challenges have been exacerbated or even added to. We're going to talk about what inline oil condition monitoring is and what it isn't. It's some of the technology is really phenomenal, but there are some things that it's not as well. We're going to discuss the benefits of using inline oil monitoring. We're going to talk about some of the inline parameters that we can measure today. The technology is there right now. Now, I want to add a disclaimer. I've made every attempt to design this presentation so it's as vendor neutral as possible. You will see the names of some vendors, okay? And that's because those vendors are vendors that I reached out to, and they provided me information to include into this webinar. It's nothing is to be construed as a direct endorsement. The absence of other vendors does not mean that they are not as good as vendors that are represented here. I just want to make sure that this in no way is a sales pitch. Okay. So you might see vendor names. It just is what it is. We're going to talk about integrating inline data with commercial data. Okay. And then we'll wrap up with a very quick discussion of the future of oil condition monitoring as I see it. It might be a little bit different, but I think I've got a good idea or a good vision of where we're going. So we'll start off with today's challenges. So what are we dealing with because of COVID-19? Well, if you attended Mike's and Rich's seminars on Monday and Tuesday, they went into a little bit detail about these challenges. So I really don't have a whole lot of different comments on that. We've got different hours. Hours have been shifted due to COVID-19. Maybe people aren't going in, or not as many people are going into the workplace. The work priority is shifted. No longer are we focused on those proactive technologies or those proactive actions. We're trying to keep that equipment running for production. A lot of times in many facilities, production has moved from what we used to make to making new things like the masks, the headgear, things of that nature. We've got to focus on PM, so preventive maintenance and corrective maintenance type activities. Okay, so and OCM, oil condition monitoring, has been sidelined in some cases. So the samples aren't getting collected, or they're getting collected, but because we're so busy doing something else, those samples aren't getting sent off to the lab in a timely manner. In many facilities, the lube techs are being diverted to other work. We don't have a situation where most of our industrial facilities have dedicated lubrication personnel, or if they are dedicated lubrication personnel, they came from another department. They came from operations, or they came from maintenance. And now, because we're diverting and changing our work, we're taking those people and putting them back into maintenance or back into operations. Okay, so the piece of oil analysis, and even in some cases, your other technologies may be experiencing the same thing. The technology is kind of being put on the sideline. In fact, these are just challenges that I put on a slide several days ago during prep. I did a quick review of some of the comments that some people put on the registration form. So here are just four what I think back up the challenges that I put up on the screen here. Number one, global recession, the potential for a global recession, thereby reducing the demand for lubrication services. Okay, we've got to, and that's a very real concern. It's a very real concern for every single lubrication or oil analysis vendor that's sitting through the webinar today. Okay, what we have to understand, and what the end users have to understand, is that there is no other task in a facility that drives reliability or influences reliability more so than lubrication or the lack of it. Okay, so we've got to make sure that we present that to the company leadership. Another concern: quality of oil sample testing and recommendations, emerging disruptive technology, and analysis of inline data. This falls right into line with the quote I've got up on the screen from Stephen Green from Stratus Technologies. So the point I want to make here is in his quote: for many, the call of the day is maintaining operational levels, while our most critical resource, people, have been constrained by needed social distancing practices and work from home requirements. It's difficult to pull an oil sample when you're working from home. Okay. If your oil sample data is maintained behind your firewall, it might be a little bit difficult to access that data from home. And one registrant had two words, and these two words are very, very powerful in my opinion. They're concerned about staying relevant. Okay, they're concerned about staying relevant. And then safety during data collection or data review and sample collection. I believe there's a technology that we'll get to that I'll introduce here that's available that might address that safety issue. So what are the labs saying? And this quote is from a laboratory. Volume is steady, however, that's expected to change soon. Okay, and we see that because pulling oil data is a lagging indicator of equipment health. Okay, pulling oil samples, sending it to the lab is a lagging indicator. All right, we're only able to tell you what the health of that machine was at the time that sample was pulled, not right now. All right, so we expect as companies change their manpower requirements for these particular tough times, that oil sample volume is going to decrease. Okay, it doesn't mean that the importance of monitoring that fluid health or that machine health has decreased. So there's got to be another way around that. So challenges that we had before COVID-19 that have been exacerbated because of COVID-19. We've always had a problem with getting the test frequency set. The most common frequency for industrial oil samples today is quarterly. I said the most common, not the right. Okay. Now, if we do quarterly sampling, that means that theoretically, if a sample is due on January 1st, we pull that sample, it goes off to the lab, the laboratory sends back the data, and that sample report is in the proverbial green status. Green, level 0, however you want to call that. In theory, that sample is the next sample is not due until April 1st. Now, I want you to think about this. We're not in a class environment, so you can't, raise your hand or comment out loud. But think about this. If we have a sample on any type system that was pulled on January 1st, the next sample is due on April 1st, is it not only possible, but isn't it probable that we could have a catastrophic equipment failure take place on March 25th? The answer is yes, absolutely yes, we can. And what's going to happen is when we have that catastrophic failure, then management is going to want to take a look at the technology data, because we're spending a lot of money on technology, whether it be vibration, infrared, oil analysis. Well, vibration may look at that, may send their data, and they say, yeah, well, we started seeing something early stages in February. It got a little bit worse at the beginning of March. So vibration saw the data. But we go walking in with the oil sample report, and we have it from January, and everything was in a green status. What that does is that takes the credibility of oil analysis and just throws it right in the trash can. Okay, so quarterly sampling just simply isn't enough on critical systems. Even if we go monthly sampling, which if all you're doing is commercial lab testing, then monthly sampling on critical systems is the recommended frequency. But even then, we're only telling you what the condition of that equipment and that fluid was at that single point in time in which you pulled the sample. Okay? Reliance on low-cost option for oil testing. I know I've got representatives from large commercial laboratories on this webinar, and I'm not saying this to put you all in a bad space or anything, but oil analysis has become a commodity. Okay, oil analysis has become a commodity. Every single lab that is on or not on this call has multiple options for end users. They've got that low cost option, but in my personal opinion, if you're going for the low cost option for oil testing, the only reason why you're doing oil testing is because you were told you had to do it. Okay, the low cost option is not comprehensive enough to tell you what you need to know about the health of that machine, the health of that lubricant, or what you need to do moving forward. Okay, so I don't care what lab the end users are using, have a discussion with those folks and make sure that the testing you're doing with them is going to help you meet your reliability objectives. I promise you they have a better test slate. Struggles for valid recommendations. And this is huge. I've seen report after report that says something like iron is high, change the oil. Particle count is high, change the oil. if the oil health is fine, if the cause of the high iron is not related to the health of the oil, then replacing the oil is going to do absolutely nothing for the cause of the high iron. Okay, it's just going to hide it. It's going to reduce the amount that's in there, but then that's just simply going to regenerate moving forward. Okay, so there are certainly some struggles for valid recommendations, and that's because we're focused on getting samples through the door. We've made a promise, the laboratories have made a promise to the end users that we're going to get your sample out within 24 to 48 hour turnaround time. And we expect that as end users, we want those reports right now. Okay. Getting the right data to the labs for appropriate alarming. I know many people in the laboratory world that work at various laboratories. So you name a lab, I probably know somebody that works there. And I've had several conversations with these folks. A vast majority of samples that go out the door in any type of an alarm status are related to what one lab calls data integrity. Okay, so we've struggled with getting the right data to the lab so the lab can set the alarms such that they're relevant for our application. And then, of course, the other challenge before COVID is achieving equipment-specific alarm levels. And I'm not talking about based upon manufacturer or model. I'm talking about that specific piece of equipment. Okay, when we do best practice alarming, each piece of equipment should have its own unique alarm value set for it. And there are some challenges behind that, but I plan to do another webinar focused specifically on alarm values. But these are the challenges that we had before COVID, and the presence of COVID and the addition of those challenges have just exacerbated these and made them even harder. So let's talk a little bit about some of the tests that a lab does. And we'll focus a little bit on the ICP and particle counting because these two tests are the cornerstones of reliability and commercial testing. Okay, so you've got ICP, also known as atomic emission spectroscopy. And ICP is just a version of atomic emission spectroscopy. So what this does is we take that oil sample and we run it through a nebulizer, and it gets turned into basically a mist and gets thrown into this plasma flame. The plasma flame is an excitation energy source, and it excites those elements. Those elements don't like to be excited, so they release that energy in the form of light. And the optics within the instrument pick up the amount of light put off at different wavelengths and then convert that value into a ppm, into a parts per million. Particle counting, today's particle counting, optical particle counting world, they're generally a light scattering type of method. So you've got a laser and the particle passes through the laser. There are different types of technology for particle counting. There's light scattering, light blockage. Spectro Scientific has their laser net finds where they also do the particle imaging, which is really neat. And the data that we get from there is generally reported through the ISO cleanliness code. Okay, and that's got its own set of problems, which we'll discuss shortly. So these are the cornerstones. And then, of course, you've got your FTIR and your viscosity, your acid numbers, your base numbers, your advanced testing, your RPVOTs, your analytical photography, and things of that nature. But those tests aren't generally, or the RPVOT, the analytical photography, those aren't generally on a routine basis, whereas the FTIR, viscosity, neutralization number, those are combined with ICP and particle counting. But let's take a look at the challenges around the ICP. Okay. Excuse me. And this is data pulled from Varian Liberty and Spectro many years ago. Okay, there's a size detection limit for ICP. It is quasi accurate up to about 5 microns. Anything beyond 5 microns, it begins to lose its accuracy. And we can see this when we look at iron in the 1 to 5 micron range. The actual concentration was 100 ppm. The measured amount using ICP was 73. And if we look at 1 to 11 microns of iron, actual concentration was 100. ICP only measured 21. And the sensitivity gets even worse if you look at different metals. I'm not saying iron's the best, but it's certainly the most sensitive based upon the chart from the sources here. Okay, so what this should tell us is that anything that we see from the emission spectroscopy data on the oil report, our actual values are likely quite a bit higher. Okay, but we don't know how much higher. We're not sure of that. All right, it all depends on the method that each individual laboratory creates within the software of their particular instrument. Now, some challenges with oil sampling and sending out to a commercial lab. This was a case study across 140 different pieces of equipment or different assets. And the case study looked at particle count, okay, basically the ISO code, and then the iron concentration. And if we just look at the iron concentration by itself, when there was a 70 parts per million alarm value, okay, 1 out of the 119 was a false alarm. There were 18 failures that were missed. Okay, and there was 1 nuisance alarm. When we lowered that threshold or lower that warning alarm to 50 ppm, 13% were a false alarm. We still had 72% missed detections and 77% nuisance alarms. Okay, and that's almost solely related to not being able to set those alarms based around the proper parameters that we should be setting alarms on. Okay, lab recommendation for ISO code 251411. So that tells us that somebody instructed either the lab or the end user, and the end user asked the lab to set the alarm value at the 4 micron level at 25 because they're not worried about those small particles. I don't necessarily think that that's the right decision, okay? But that's on a case-by-case basis. It all depends on what types of small particles they're ingressing into the system, all right? But these are just some of the most common challenges that we see with standard or routine, periodic, pull a sample, send it off to a laboratory. Okay, so inline real-time oil condition monitoring. There are technologies available today. These technologies are not widely known. No, I was just on a conversation with my colleague from Amory, Mike Johnson, just earlier this week, and he was on a call with a client. And Mike was telling this client about the webinar series that we are doing this week. And the client stated, "I'm glad to hear this is available. No one is talking about this." There are a lot of different available sensors out there. Okay. The challenge is that there's not really anyone talking about this as a technology as a whole. Okay, and why? Because everybody's focused on vibration. Everybody thinks vibration is the be-all, end-all to monitoring reliability. However, vibration tells you that there's a problem that is present. Vibration tells you that we have reached or bypassed point P on the PF curve. Okay, proper oil analysis can tell you have a condition which will lead to point P on the PF curve if we don't address that condition right away. Okay? These sensors, the oil condition monitoring sensors, another reason why there's a struggle getting this technology out is because of the cost. There are vibration sensors that you can get for $25. Now, obviously, you're going to get what you pay for. Okay? The most common price threshold for a single vibration sensor is $250. Okay, Of course, you need multiple sensors unless you're using a triaxial, but that's a whole nother webinar, a whole nother duty expert that needs to have that discussion. Oil sensors are not $250. The requirement of monitoring oil sensors is not $250, and it won't be for quite some time. So they're pricey. But let me ask you this: in order to justify putting on inline sensors on your systems, you have to ask, what's the cost of failure? If this inline sensor can identify an early potential failure one time, will that cover the cost? I would be willing to bet that in every instance, if we're looking at critical systems, the answer will be yes. Okay, and I've already mentioned that there are multiple providers in the marketplace. Everybody is waiting, and this sounds really bad because I don't mean it to. Oil analysis inline sensors were really waiting on a situation like what we have today, where people needed something to realize, wow, what else can we do? It's unfortunate that it took this type of situation across the world to occur, but it is what it is. In fact, Stephen Green from Stratus Technologies, again, he says the current situation calls for leaders to lean in and adopt new approaches. This does not mean the tolerance for risk increases, however. Safely maintaining and scaling operations requires capabilities that enable greater and more reliable remote and secure monitoring and control of critical systems. So the types of capabilities that we have out there today, or that are out there today, include ferrous and non-ferrous wear measurements, particle counting. Either if you want to stick with the ISO code, that's available. If you want total particles in ppm, that's available. There's breather condition technology. There's oil level indicators, fluid health, all the way down to our wonderful viscosity. We've preached for years that viscosity is the single most important property of a lubricant. Well, there's a inline viscosity sensor out there on the market today. And of course, temperature, and then even automatic sample collection. Now, I want to point out, I highlighted this verbiage in red. In my opinion, and this is my opinion only, real-time monitoring is not meant to replace commercial lab sample testing and analysis. It's designed to be used in addition to that testing and analysis. Okay, I'm not going to sit here on this webinar nor stand in front of a bunch of people and say that if we do inline monitoring, all your lab analysis can go away. And I would challenge anyone that would say that, okay? Because there's information that we get from the commercial laboratory that today we can't get from an inline sensor. Does that mean that at no point in the future will this statement be false? No, at some point, as sensors mature, as algorithms mature, that might be the case in the future, but I don't see it anytime in the near future. Okay, so let's talk about ferrous particle counting first. Now here's a case study on a gearbox. Gear tooth breaks. Okay, so what we see on this graph is a very large amount of metal generated over a very short amount of time. Okay, and we can follow the graph from the left to the right. And I know the numbers are small, and I'm not wearing glasses, so I can't read them. But there's several days between each data point. But you can see, because it's live monitoring, we see that values were very, very low. And then all of a sudden, values shoot way high. So there's an immediate breakage. Something happened, and it happened right now, very little, if any, warning. Now, if we look at the scale, our red line is iron 4 to 500. Pretty doggone large particles. Okay. And this happened in a matter of hours. Okay. Not days, not months. We could have pulled a sample yesterday and everything would have been fine. And now all of a sudden we have a catastrophic failure the very next day. What does that do to the credibility of oil analysis? Okay, it definitely throws it in the trash. If I'm a maintenance manager, I'm going to be really upset if that's the case. Okay, and we all know anybody on this webinar right now that's worked in oil analysis for any real length of time has seen instances where we pulled an oil sample and there was just simply no supporting data that there was an issue, and the equipment wrecked a week later. Sometimes it wrecks while the sample is still out to get tested. Okay, so here's just an example of the benefit of monitoring that ferrous wear in those applications where we can expect to see ferrous debris as the primary wear metal. Okay, so if we look at the wear metals in review, if we consider the size and even the weight of some of those particles, routine oil analysis would have never even identified that there was an issue unless the test slate was defined correctly. In other words, we weren't doing the low-cost option testing. But if the test slate were correct and if the sampling interval or the sample was pulled at just the right time, we might have been able to identify that there's a catastrophic condition. But how much time does it take for you to get the work order, to assign the work order to somebody, for somebody to go out and pull the sample, for that sample to get labeled correctly, get packaged up, shipped to the laboratory, and then the laboratory get the data back to you, and then you have the time to log in and read that data? Okay, that right there could be as much as a week or two. A lot can happen in that short amount of time. So let's talk about the next door neighbor to ICP, which is particle counting. People like me, people like other trainers that have taught about lubrication and oil analysis and contamination control, we've been talking about the ISO cleanliness code for years. We've been pounding people with this information. You've got to set a target. If you're below your target, you're great. If you're above your target, you must do something about it. Target, target, target. And people are so focused on the target cleanliness code that some laboratories only report the ISO code and not the raw data. Well, I say shame on us, to include myself. We have done a disservice to the end user, in my opinion. Okay, and now we're kind of stuck with it, maybe. And the reason I say that it's a problem is, any of you that have gone through a training course, this has been pointed out to you. Those of you that may be seeing this for the first time, I'll dive into a very little bit of detail. If we look at the ISO table on the or the range table on the right side of your screen, we see that the ISO values are on the right, and then the range is on the left and in the middle. So for instance, the ISO value of 20, on the low end is 5,000 up to and including 10,000. So basically 5,001 particles per milliliter up to and including 10,000 particles. So not only does it double between ISO ranges, but it doubles within itself. So you've got it doubling on the low end, doubling on the high end, doubling within itself. So you can have a significant increase in the raw data without changing an ISO value. So if all you're looking at is, if all you're focused on is your ISO code, you are going to have a missed opportunity. And let's take a look at how that works. This is an excerpt from an article that I wrote several years ago. So I've been talking about this for a really, really long time. Now, if we look at the tabular data, this is off of a hydraulic system. Okay, if we look at the tabular data, this is directly from the oil display that we had at the time. You go from right to left. So our oldest sample is on the right, our newest sample is on the left, and then the samples in between, they are what they are. And we see that our November sample, okay, our November sample dropped significantly. Now, if we don't look at December, we can say, okay, they must have changed filters, they must have done something, okay, flushed out the reservoir, they must have done something. But then December rolls around and it pops back up about where it was trending, okay, a little bit higher if we only focus on the ISO code. Now, all you analysts out there that are on the webinar right now, I know what you're doing. You're looking at the raw data, which is what you should be doing, but you're looking at the raw data saying, well, September, October, there's actually a big increase from October to December, so it's not really in line. However, our end users mostly focus on the ISO code because that's what we've told them to do. So if we were to graph the change onto a standard graph that we see on the right, and let's focus on that 4 micron level because this is a hydraulic system. Those silt-sized particles are the ones that are going to clog that and really cause a problem. Okay, so if we just focus on the 4 micron level and we graph, September was 22, October was 22, November, pretty much an outlier in my opinion. December, it's back up to a 22. So from an ISO code at the 4 micron level, it's not really changed. But has it? Has it? Now, what I like and what I presented many years ago is potentially changing how that ISO value is reported. Okay, so if we use that ISO 20 value, which was between 5,000 and 10,000 particles, we subtract that, we divide it by 10, and we simply add a decimal. If we add a decimal, so you're creating basically a log 10 scale. So if we add a decimal to that ISO code, now we can trend that. Now we can graph that because some people like graphs, some people like pictures, some people like numbers, okay? But there we can understand that there's a big difference between a 20.0 and a 20.9. That gives us trendable data. That gives us some place to go, okay? So what we want to do is moving forward, because I don't think ISO is going to change the ISO code, not anytime soon. It's still going to be 4406, 46, and 14. It may change, it may not. It is what it is, okay? But we as end users, we want to start looking at the data and tracking that data and monitoring how that data changes over time, right? Now, how can we do that? Well, this becomes the fun part. We can actually do that with inline sensors. The inline sensors that are able to monitor the raw data and report the raw data in addition to the ISO code, we can completely ignore what's on the actual screen of the inline particle counter itself. We just have a software environment that does all of this stuff for us. Okay, I like to use the common term. You know, there's an app for that. There's an app for just about everything these days. So that's particle counting. Now, we even have breathers. We even have when I say we as an industry, there are breathers out there now that can be connected to the cloud, that can actually report to you what your consumption is. Okay, you can monitor the consumption numerically instead of just visually. You can actually monitor it and then data mine the information provided back to determine trouble spots. Okay, so in this example, breathers installed on 2 wind turbine gearboxes. Okay, selected at random, both gearboxes on the same site. Breather was installed on asset B13. The deskit was being consumed at a very high rate, 70% consumed in 10 weeks. It was replaced and the consumption actually accelerated. Okay, whereas the breather installed on asset B50, after 7 months of use, only 2% of that breather life was consumed. Now, why do we care about that information? I'll tell you why I care, because I want to go out that tells me that there is something fundamentally, operationally, environmentally different between those two turbine gearboxes. They may appear on the surface to be operating in the exact same environment, but they're not. Something is different. So that gives me an idea to be able to go to 13 and try to figure out what's different about that than B50. Okay. It allows us to focus our efforts so that when we go out to this equipment, we're going out because there's a reason to go out, not just because, well, we've got a work order that says we've got to walk around the facility. Okay. Let's walk around the facility and do value-added tasks. There are even remote oil level monitoring technologies out there. We've got an intake oil level sensor on the right, and our friends at Trico have come up with an apparatus that fits around the constant level oilers and reports that oil level remotely. Okay, and now what they're monitoring is just the oil level in that constant level oiler. But when you have manpower requirements to go out every day or every week and do visual oil inspections, the amount of equipment that a lot of our facilities have requires a significant number of man hours just to monitor that oil level. Okay. Now imagine if we could log into a single application and simply few strokes on the keyboard, few mouse clicks, see a list of everything that's got a low oil level. Now, when we send our people out to the facility, out into the plant, they know exactly what lubricant to take with them. They've got a good idea how much. They know which breathers to take with them, especially if we can get all of this into a single operating environment. Oil health monitoring. This is key, because when we look at root causes of failure, number one root cause of failure in industrial equipment is particle contamination. Number two is moisture contamination. We wrap those up into one big contamination category. And then we have fluid health related issues. Now, what do I mean by fluid health? Well, leaving this stuff in there way too long, it begins to oxidize, viscosity changes. Somebody doing a top up with the wrong fluid. I don't care how much labeling we do, sometimes it's going to happen. Okay? So there are several instances that can change or modify oil health. Now, a very common sensor out there is a dielectric sensor. Okay? It measures that parameter. What's the dielectric change? Okay. But we've got technology called impedance spectroscopy that actually induces multiple frequencies into the oil so that we can monitor multiple Nyquist curves. All right. The more data that we have coming out, the higher the confidence level we have in making our decisions. If anybody here has ever heard me talk about data analysis with commercial lab data, I have always said, don't ever make a call based off of a single data point. You always look for a confirming piece of data, even if it's just a minute change. Always look for a confirming piece of data before you make a call. If you have to request a second sample to confirm that this data is not right. But rarely do you want to make a call based off of a change of one data point. Well, with impedance spectroscopy, we've got multiple frequencies. So if we follow that trend of all of these, then it increases our confidence that there is, in fact, something wrong, and we need to go out and take some type of action. Okay. Also, viscosity. There's a viscosity sensor out on the market as well. Now, in my opinion, how much do we need to measure inline viscosity? I've got my opinions around it, because if you ask any laboratory out there, how many reports go out because the viscosity changed? Yes, it's the single most important property of a lubricant, but it's a very, very small percentage of oil reports go out into an alarm because the viscosity changed. If the viscosity is different, chances are it's because a lubricant was changed, a lubricant type, a viscosity change was made, and it simply wasn't reported back to the lab. That goes back to the data integrity issue that I was talking about previously. So here's a case study of remote oil health monitoring. We see on the graph that we had normal degradation of that fluid, and then all of a sudden we had a big drop. Okay, and it was identified just like that. Now the end user had to make a decision on when and how they were going to go about making the change, but we see that once that oil really got to a condemning point, they did the oil change and everything was back to normal. Would we have seen that in oil analysis, in standard laboratory analysis? The answer is yes. But the only way that we would have seen it as early as is detected through the sensor technology is if we happen to be there and pull that sample right at that time. Otherwise, we would have been much further down that PF curve by the time that we identified that there is a problem. Okay, and there are three categories of oil analysis: machine health, fluid health, and contamination. The machine health operates in the predictive maintenance zone. The fluid health and the contamination operate in the proactive maintenance zone. If we can monitor the health of the lubricant and the contamination level before it causes damage to the machine and do something about it, then we're being proactive. It's difficult to do that in standard laboratory oil analysis. And somebody mentioned safety during sample collection. A organization out there, a gentleman, Bill Gillette, he created an automatic oil sampler. So where safety or manpower becomes an issue, we can simply put this device on the system, tell the device what that interval should be, and it automatically fills up a sample bottle for us. Okay, so we could have this auto sampler mounted someplace that is accessible, and then have the oil piped to it. And of course, it needs to be in a loop so we don't have a deadhead location. And as that oil flows, if the programmed interval comes about, it just simply fills up the bottle. Okay, excellent opportunity to address those situations where safety or manpower becomes an issue. Now, data display and management. Some of our sensors are designed to just simply be installed and display the data at the location, okay, at the location of install. Some of our sensors, most of our sensors, have the ability to be tied into some cloud or network type of application. And there are some benefits to both, okay? The benefits of having on location, you get better total buy-in. The people doing lubrication buy into the process because they still feel involved because they are involved, okay? It still allows them to do something with respect to visual inspections, because when you have lubrication personnel that are assigned specific areas, they take ownership of those areas. So they want to feel like that they're still involved in that process. Okay. And of course, the cloud or network benefits, well, custom alarm notifications. You can tell whatever application you're using that I need a notification if we bypass this point. Okay. It gives us the ability to have historical trending for troubleshooting. Go back and find out when the problem really started. Because if we can go back and find out when the problem really started, when we identified it with a sensor technology, then that helps us begin to integrate the capabilities between oil analysis sensors and vibration data. Okay. And then, of course, data access from anywhere. It gives us a true remote situation or true remote capabilities. Anybody on this call, if you're not currently at your place of work right now, you could simply log in to your cloud, whether it's installed behind the firewall or truly up in the cloud, then you can monitor the health of your equipment from anywhere. So the strategy, this is the strategy according to Matt. This may change depending on who you're talking to. This may change based off of your own reliability needs or objectives. For mid-level criticality equipment. So equipment that, yeah, we would like to monitor, but it's not going to shut down the whole facility. Okay? But we like this whole Internet of Things thing. Okay? Particle counter, potential moisture if you have a potential moisture problem, and maybe just have that visual indicator at the equipment. Okay? Now, if you're worried about trending and you want to be able to do that truly remote, then obviously the visual only is there's got to be something else. You've got to have the real-time trending. All right. So, and that's where we would say mid to high level criticality equipment, particle counting, moisture, have a visual at the location, send that data someplace to allow you to have real-time trending and alarms. Your high level criticality equipment, particle counting, moisture, ferrous, non-ferrous capabilities, and again, visual at the location, and real-time trending and alarm capabilities. And then, of course, your very high-level criticality. You want your particle count, moisture, ferrous, non-ferrous, oil condition, and again, visual at location, real-time trending. This strategy can be modified depending on your needs. And the terms mid-level criticality, mid-high level, very high level, those are all relative terms. I cannot define for you what those terms mean. They're all 100% consistent based upon your criticality assessment values and what you and your team define as very high level, et cetera, et cetera. Okay. What I would encourage you to do, if you're even considering a continuous monitoring strategy, put the sensors to the test. Focus on your problem children. Okay. If you've got assets that are just always a problem, let's focus on those. Because imagine if continuous monitoring can help you fix these problem children, imagine what it can do from a monitoring perspective for everything else. So, future of condition monitoring. Critical systems using some form of real-time monitoring to trigger comprehensive lab testing. So I think we're going to move to a true condition-based oil analysis process. All right. It's not going to happen this year. It's not going to happen next year, but it's going to begin to happen. Okay. It's going to begin to happen. We're going to move from this, what some places might call a screening test. All right. Because who cares? What's the screening test really telling us? Let's get in there and let's have real data so we can make real decisions. AI and machine learning becoming more than marketing acronyms. I know everyone on this call has seen companies promoting artificial intelligence, machine learning. They're not doing that yet. Okay, I promise you they're not doing it the way it's being marketed yet. They're working on it. I guarantee you they're working on it. In fact, commercial labs have been using some form of artificial intelligence and machine learning for 20 or more years. Okay, and they're getting better. But right now, there's not an application out there that really has the amount of information needed to do full artificial intelligence and machine learning. It's just not there yet, but it will be. Integrating data derived from inline sensors with commercial lab data. That is going to be the key. Okay, and to be effective, this has to go beyond having the data on separate pages or dashboards. We don't want a system where we've got one page for our inline data and then we have to log into something else or another page for the online data or the commercial data. The most value is going to be when we can combine that data together and truly derive condition measurements based off of that combined data and then making those recommendations moving forward. So are we there today? No. Are we working on it? You bet we are. Okay, you bet we are. So here's my contact information. I want to thank you for your time. Be safe, stay healthy. Michael Holloway, while you're jotting down this information, has a few wrap-up words for you. Thank you.
Matt, thank you so much. That was fantastic. Love listening to you talk about this stuff and all kinds of other things as well. Guys, thank you very much. At the end of this, please don't sign off quite yet. We have a couple quick questions to ask you. Definitely. We also provide these we have recordings of this presentation too, if you'd like. And tomorrow, we'll be talking about competency development, the deployment, and establishing those things. So please, same bat time, same bat channel if you can. Look forward to it. Look forward to your comments. And as always, contact us if you need more information and recordings. Thank you so much. I appreciate it.